All right, so today is the 16th of April. This is York College Chemistry 108, and we will start on Chapter 7. So Chapter 7, the class kind of takes a little bit of a turn now. So eventually we will get back to, moles and energy and all of that. But now we're going to take a look at what we can think about as atomic structure. Right, up till now, we've thought about atomic structure kind of like this. The atom has a nucleus. Right, the nucleus has protons and neutrons, and around the nucleus there's this kind of bunch of electrons that are kind of floating around. That's all true. But kind of in the early 1900s, scientists started to take a much closer look at very, very small particles, including atoms and electrons and a lot of the things that we're talking about. And what they found was that the behavior of those particles didn't really match what they had already understood. And so that's why this background is here. Who knows where this is from? Matrix. Right. And so in the matrix, the physics of the matrix gets all screwy, right? It gets all confused. And so when they fire the gun at Neo, he's able to dodge it and all that stuff. That really shouldn't be happening, right? And so that was the same kind of thing happened when scientists started taking a close look at these really, really small particles. And out of that came a new understanding of really physics and really kind of the whole nature of matter. Largely today that gets called quantum theory. So this is what we've understood up till now, right? The nucleus is made up of protons that have a positive charge, neutrons have a neutral charge, and around the nucleus you have electrons. Now, this is the common kind of what you see on TV and that kind of thing. And while there is a little bit of truth to that model, right? You have a nucleus in the middle, you have electrons, and the electrons have some kind of definition to where they have to be. That's really not how atoms behave once you start looking at a detailed level, right? So this is kind of one way that we can look at atoms. And where does that come from? Well, you have this guy here, right? And he's kind of like your nucleus. And you have him in this kind of big, enormous wave that's much, much bigger than him. And that can represent in some sense, the electron. And so we'll see there's this, what we can call duality, what we can call kind of a very strange equivalence between matter and waves. And that equivalence gets stronger and more pronounced the smaller you get. And so the smallest things that we've thought about so far in this class are electrons. And so a lot of what we're going to do moving forward has to do with how electrons and other pieces of matter actually have these kind of wave-like properties. And as a result of that, what happens to them? Or as a result of that, what are their properties? So we'll review some things, right? So matter, anything that has mass and takes up space. Remember that from Chapter 1. Electromagnetic radiation. This is something we haven't really talked about yet, and we've talked about solar energy or radiant energy, which comes in the form of light, right, when we talked about thermochemistry. But we haven't really defined or talked about electromagnetic radiation. So electromagnetic radiation is something most of us have heard of, right? But probably we haven't thought deeply about. So it's energy that exhibits wave-like properties as it travels through space. And the most common type of electromagnetic radiation that we kind of interact with, or the most obvious anyway, is light. Right? Light, as long as we can see, we can sense the light. But things like radio waves, microwaves, UV light, those are all different forms of electromagnetic radiation. And so two things that we will note here. Electromagnetic radiation is wave-like, so it has properties of a wave. And when we talk about waves, you want to think like a sine wave that you learned about in math, cosine, right? That kind of shape. And the other point here is electromagnetic radiation interacts with matter in unexpected ways. And those are some of the matrix-like things that we'll get to. I realize I haven't put up slides in a while, so I'll do that for the last couple of chapters also. Okay, so waves, right? So we said kind of sine-like waves or cosine-like waves. Let's define some things. Waves have some properties that you can use to identify a particular wave or a particular type of wave. And so one of them is going to be called its amplitude. Right, so, pointer please, yes. So the amplitude defines the distance from the baseline to the peak, or from the baseline to the trough, the valley, the baseline being kind of like the midline of the wave. The wavelength is the distance from, because the wave is repeating, from one point on the wave to the next equivalent point on the wave. That's sort of the length of one repetition of the wave. It's called the wavelength. And the way we draw it, when you visualize it, it's there. But you have to imagine that this wave is traveling, right? It's moving. And so the wave has a direction. And so if we look over here, we have wavelength, we have amplitude. And this second wave compared to the first wave, the wavelength is smaller. Right? So now if we consider like this box, for this top one with the longer wavelength, we get 1, 2, 3, basically 3 and a little more individual repeating units of the wave. On this bottom one, how many do we get? We get 1, 2, 3, 4, 5, 6, 7, 8. Well, we get almost 10 individual repeating units of the wave. So we can say this one within this box, the lower one repeats more frequently. Or in other words, it has a higher frequency. And so that's another word that, or another term that we're going to think about. So wavelength is the distance between identical points. Amplitude is a vertical distance from the midline to the peak or the trough. And frequency is the number of waves that pass through a particular point in a particular amount of time. And it's usually reported as 1 second. So wavelength in chemistry and physics and science in general is given this Greek letter as its abbreviation, and that's a Greek letter lambda, lowercase lambda. We don't have to write it with all the kind of curly things in it. Kind of an upside down Y is how we would write it. Amplitude, we talked about amplitude, we'll find out doesn't have that much of an effect on what we're going to talk about moving forward. And frequency, it looks like a V. It's actually a Greek letter called nu, and it's kind of drawn like a curly V. So frequency and wavelength have a relationship, right? If you look up there, what's the relationship between wavelength and frequency? shorter wavelength, higher frequency, right? Shorter wavelength, higher frequency, or longer wavelength, lower frequency. That is assuming the speed of the waves as it's propagating through space of the two waves are the same. So, wavelength, what kind of units do you think wavelength is going to have? Yeah, so it's going to be a unit of distance. So meters, millimeters, centimeters, nanometers, and so on. Frequency is very interesting. It has a unit of hertz, or 1/seconds equals hertz, like the car rental company, or Hz. That means per second, right? So hertz tells you how many of something happens per second. And so frequency is the number of waves that pass through a particular point per second. That's how many per second. Can you see that? No, you can't. Okay. The speed, often abbreviated u, of the wave is lambda times nu. Does that make sense? Lambda is how long the wavelength is. Nu is how many of those wavelengths you have per second. So you put those together, you get the speed. And let's think about units. What's lambda? It's something like meters. What's nu? Per hertz, or 1/seconds, per seconds. So if we do, let's say the lambda is in meters, right? We do lambda in meters multiplied by nu in 1/seconds. What do we get? We get meters over seconds, or meters per second, which is indeed a speed or velocity. Question so far? Okay, so like we said, there's a relationship between these things. So this is kind of general waves. Any kind of wave is going to have these properties, whether it's electromagnetic radiation, or whether it's a sound wave, or whether it's a wave in the ocean, or whether it's a wave on like your violin or your guitar or whatever stringed instrument you're playing. They're all going to have the same properties, or these properties can be used to describe them. We're going to look now specifically at electromagnetic waves, right? Because that's where we're going, right? How electromagnetic waves interact with matter and define matter and all that stuff. So, 1873, it was proposed that visible light consists of electromagnetic waves. So that means there is an electric field component and a magnetic field component. We don't have to really think, and they're at right angles to one another, right? So if the electrical field component, the red, is up and down, the kind of funny green here is kind of in and out of the board, and it's moving in the x direction. And so the thing is, the frequency and the wavelength of both components are going to be the same as one another, right? So very often we don't draw it like this because it's hard to draw. We'll just draw one wave that represents the whole thing. Electromagnetic radiation is the emission or the transmission of energy in the form of electromagnetic waves. So it could be light, for example, right? The light that's coming out of the lights in the ceiling, or the light that's coming out of the sun, is in the form of electromagnetic waves. And it was also discovered that light has a particular speed. Right? We may have heard of the speed of light. We've heard that it's physically impossible for everything to cross the speed of light, right? So anything any projectile, any rocket, anything can't go faster than this. and so it's the speed of light in a vacuum. If you go not through a vacuum, it changes kind of very slightly. So we assume that whenever we're talking about the speed of light, unless otherwise kind of directed, that it's 3.00 times 10 to the 8th meters per second. And this is one of these things where it just happens to be 3.00, right? We kind of got lucky that way. But it has significant figures, right? If you go look it up in a handbook, it's going to be 3.00 something, 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 something. That's not all zeros. So we're going to use 3.00. It has 3 significant figures. And so, remember this from the last slide, lambda times nu equals c. So we put this equals u, equals the speed of the wave. So if the wave is light, or if the wave is electromagnetic radiation, this applies not just to light we can see, but all sorts of electromagnetic radiation, then the wavelength times the frequency equals c, right? Equals 3.00 times 10 to the 8th meters per second. So if we say, let's do a problem. Because we can. You know what, let's not do problems yet. Let's go on to the next slide. So this slide describes in a little more detail electromagnetic radiation. So electromagnetic radiation includes things you may have heard of, like gamma rays. It's not something that they just made up for the comics, right? There's really such rays as gamma rays. They're very high in energy. Right? X-rays, we know about X-rays. Right? UV rays, those are that's the light, right? That's the radiation that gives you a tan or gives you a sunburn. Visible light, right? That's what we can see. And we know that if we take visible light and run it through a prism, or if you're lucky and you look outside after it's raining, that visible light can get broken up into a rainbow, right? And so you have different colors within the visible region of what we call the electromagnetic spectrum. And then you have infrared, right? Infrared is typically associated with heat. And so you know, when you see like the military folks or you know, put on with those night vision goggles, right? Those are special goggles that are able to sense infrared. So even if there's no visible light and you can't see anything, if there's something alive and moving around, it's giving off heat, you'll be able to sense that. So then microwave, right? Those are the same microwaves that cook your food. Radio waves, those are the same radio waves that, you know, you listen to on the radio. And so there's a spectrum, and you'll notice the frequency or the wavelength, of course, as the frequency, the wavelength, goes from small wavelength to large wavelength. The wavelength gets larger as you go 10 to the negative 3, 10 to the negative 1, 10 to 0, 10 to the 3, 10 to the 5, 10 to the 7th, and so on. As the wavelength gets bigger, the frequency gets smaller. It goes to 10 to the 20th, 10 to the 18th, 10 to the 16th, and so on. And so this is quite a broad range, right? So 10 to the 20th is basically followed by 20 zeros, right? It's an enormous number. All the way down to 10 to the 4th, we can even get smaller than that. And then 10 to the negative 3 in terms of nanometers, that's really, really tiny. All the way up to 10 to the 13th, right? That's enormous. So the electromagnetic spectrum has a very large range. As you move forward in chemistry, if you move forward in chemistry, right, you'll learn about different applications within chemistry for ultraviolet light, for infrared light, for microwave radiation, and so on. That typically comes like in organic too, if those of you who are going to take it. Okay. Right, that's the visible light. So now let's do the problem. So let's say there's a particular type of light, a particular beam of light that has a frequency of 6 times 10 to the fourth, 6.0 times 10 to the fourth. What's the wavelength associated with that frequency? And does that frequency fall into the visible region? Who has an idea how to do this? Yes?
It's the speed of light divided by that.
Okay, you're always like 3 steps ahead. So the first thing is we're going to, that's not wrong, but it's going to be lambda times nu for an electromagnetic radiation equals C. Right, and so C is 3.00 times 10 to the 8th meters per second. And remember, what is Hertz? Hertz is 1 over seconds, right? So we're trying to find lambda, and nu is 6.0 times 10 to the 14th, 1 over seconds, right? I want to solve for lambda, right? So when I solve for lambda, what am I going to do? I'm going to divide both sides by this. And so when I divide both sides by this, I'm going to get lambda equals 3.00 times 10 to the 8th meters per second. And when I divide by this, what can I do? I flip it and multiply, right? So I'm going to do over 6.00 times 10 to the 14th, 1 over seconds. The seconds and the seconds are going to cancel. What I have left is meters. So it's going to be 0.500 times 10 to the 8th minus 14. So it's going to be 10 to the minus 6, right? Meters. Or 5.00 times 10 to the, it's going to get bigger, it's got minus 7th meters. It asks for the wavelength in terms of nanometers. And so if I take my 5.00 times 10 to the negative 7th meters, how many nanometers in a meter? Right, 10 to the 9th, or I can say 1 meter equals 1 times 10 to the, no, 1 nanometer equals 1 times 10 to the negative 9th meters. It's going to be 5.00 times 10 squared equals 500 nanometers. Questions there? Yeah. Oh, 4. That's why. That's funny. Okay. I'm just kidding. See, that's why you need better handwriting. So this is going to be 10 to the 4th, right? Up here. And then that's going to be equal to 10 to the 3rd meters. So I didn't have to erase that whole thing. Times 10 to the 3rd meter. So meters, 1 times 10 to the negative 9th meter equals 1 nanometer. And that's going to give me 5.00 times 10 to the 12th, right? Nanometers. So how do we know whether this falls into the range of visible light or not? Well, we're going to flip back, and we're going to say 10 to the 12th nanometers. 10 to the 12th nanometers is way up here. So it's not. Right? Where does visible light fall? Visible light falls from 400 roughly to 700 nanometers. Right? We don't have to learn most of these, except we should know that visible light falls kind of here, 400 to 700. And blue is on the 400 side, and red is on the 700 side. So no, it's not part of the, does not fall within visible light. Questions? Whoa. Okay. So the next part of the lecture kind of deals with, now that we have kind of a basic understanding of what waves are, it's really kind of hard to talk about all of these without, well, let's say in a short period of time that we're going to try to talk about them in. But here's kind of these are some of the experiments that led to sort of like this matrix-like understanding of matter. So the first problem, or the first mystery, was what's called the heated solids problem. And it's also known as what's called the black body radiation problem. And so basically, black body is it can be approximated by a piece of metal, right? And so you take the piece of metal and you heat it up, and what happens? When you take a piece of metal and you heat it up, what happens to it? It starts to glow, right? You've maybe seen pictures kind of like this, right? This is some kind of molten iron or something. And as you heat it, it starts to give off radiation, right? It starts to radiate its own energy, or it starts to radiate the energy from the heat, right? And so there is a problem here, right? So there's many things that we show you. Nearly all of them you have to understand and be able to do stuff with. This is not one of them. Okay, so what's the problem here? The problem here is that as you heat your metal, the more you heat the metal, the more energy it should give off, right? That's kind of the idea. But that's not really the case. That's not what happens. Well, that's not true. Let's put it this way. The more energy it gives off, the more it should move towards that side of the graph, right? That side of the electromagnetic spectrum, as we had it set up before. But it doesn't, right? It gets, eventually, it doesn't keep going up. And so where you start, this is what you would expect, and this is what was observed. And so down here, it looks about the same. What happens actually is there's this formula that describes the black body radiation. You don't need to know it. And there's this formula that's what we actually see, right? This is what people thought it was. This is what actually happens. You can see the first part is about the same, right? 8 pi nu squared over c cubed, 8 pi nu squared over c cubed. The thing was, as this got higher, this factor here kind of came into play. People never knew about that until 1900. You can say that's a long time ago, but actually there was a long time of time before 1900, right? And so what comes out of here is this letter here, H. H is a term known as Planck's constant. Right, so, yeah. So the radiant energy emitted by an object at a certain temperature depends on its wavelength. And so what comes out of this is this constant called H. And the kind of conclusion that gets drawn is that energy, so the kind of conclusion that gets drawn is that the energy that's emitted is equal to this constant H times the wavelength of the light that's being emitted. So H has a particular value, 6.63 times 10 to the negative 34th joules times seconds. Right? It's if you want to, I guess the simplest way to present this is that if you want to know more about it, become a chemistry major and take physical chemistry 2. But they also noticed that the energy or the light is emitted or absorbed in discrete units, right, which are called quantum. What does that mean? That means only specific amounts of energy could be blah, blah, blah. Okay, so a discrete, what does discrete mean? Discrete means something that's can be broken apart, right? So discrete units, discrete pieces. And so this is kind of the way in to what we're going to see. This is going to make more sense as we move forward a little bit. Okay, so the second thing that happens, this is something that's a little easier to explain. It's called the photoelectric effect, and this was actually solved in 1905. So this is 5 years after Planck, and it's and this was solved by Einstein. Right? So this was some of Einstein's earlier work. Okay, and so here's the thing, right? So when light shines on a metal, you can imagine, okay, metal surface, it gets hit by light, energy goes in, something can happen. Right? What can happen is actually that electrons can be ejected from the surface of the metal. Right? So the light goes and hits the metal, and with sufficient energy, the light can knock out an electron from that metal. And so what was observed is that sometimes you shine light on the metal and an electron pops out. Sometimes you shine light on the metal and the electron doesn't pop out. So what people kind of thought was, okay, if you kind of have like a dimmer switch on your light, right, and you have it low on the dimmer switch, then if there's no electrons popping out, if we turn the dimmer switch higher, then you'll get electrons to start popping out, right, because you're putting in more light. But that wasn't the case, right? The case was that regardless of whether the dimmer switch was high or low, right, whether the light was really, really bright or kind of dim, whether or not the electron popped out depended on the frequency of the light. Remember, frequency is correlated to something like color. Remember, the blue or the red has, or the blue has high frequency and the red has low frequency. So if you had a particular metal and you had a little tiny bit of blue light, you might be able to pop out electrons. If you switch to red light, even if you turn the light up real high, as long as there's red light, nothing would pop out. So the frequency, or what we can think about as color, was what defined whether the electron popped out or not. The conclusion that was made was that in some sense, the blue light must have higher energy than the red light. And it's that energy associated with the blue light or the red light that determines whether the electron is going to pop out or not. Right? Remember, this is what Planck comes out of Planck's constant. E, energy, equals h, a constant, times the wavelength, the frequency, nu. So the higher the frequency, the higher the energy. And so the higher the frequency, and so once you pass this threshold, let's say if we go back to here, right? This is low wavelength, high frequency. This is high wavelength, low frequency, right? So let's say no electron, no electron, no electron, no electron, no electron, no electron. Here, the electron starts popping out. But once you get here, the electron pops out and it just kind of floats. And then as you go and add more and as you go more and more toward the blue, the electron that pops out starts moving faster and faster and faster and has more and more and more energy. That's because the energy of the light increases. And so some of the energy is required so some of the energy is required just to pop the electron out. And then as you pass that energy, the energy that's going in makes the electron that pops out more energetic. It gives it more speed, gives it more oomph. And so this had a few things that came out, a few items that, or a few conclusions that came out. One was that light has both a wave nature and something like a particle nature, right? Because light clearly has a wave nature, right? It has a wavelength, it has a frequency. Those things can be measured, but it also behaves something like a particle. So let's go back to here again. Right. We were saying as you increase the frequency, you increase the energy of the electrons. Now what if we're out here, right? The electrons are popping out. What happens if now we turn the dimmer switch of the blue light from low to high? Right, so at first we just have a little bit of blue light going in, and what if we turn that blue way up high? The energy of the electrons is not going to change. What's going to change is you're going to get more electrons. Right? So what that kind of suggests is that you have more of these, what we're thinking about as particles of light that are striking the metal and making the electrons pop out. So,
well, why is the energy of the electron not affected then?
Because the energy is not defined by the dimmer switch, it's defined by the frequency. Right? The dimmer switch just tells you how the frequency tells you how energetic the particles, or that are called photons, right? The frequency tells you how much energy they have, how much energy each one has, and then the dimmer switch tells you how many of those particles are there. Right? So the more particles you have, the more electrons you can knock out. But all the electrons have the same energy if the light is all the same frequency. Yeah?
When electrons change from like excited state to ground state.
Don't talk about that yet. What's that? Sorry, go ahead. No.
No, the question was that in thermochemistry, when you learned that energy can't be destroyed, it can only be constant change.
Yeah.
Then does that happen when it goes from the excited to ground state, or does it die off?
So, okay, so we don't know about that yet, except maybe you do. Energy is not created or destroyed, right? If the electron changes energy, if it absorbs energy, it goes higher in energy. If an electron reduces in energy, it actually has to emit energy. Right, so the energy what's that?
So the thermodynamics law doesn't apply to this.
Oh, it does. Oh, it absolutely does. Because if you go, okay, so here's the way it relates to thermochemistry. If your system goes from a high energy state to a low energy state, what has to happen? It has to release energy. So that's kind of what happens. That's what we might call like fluorescence, for example. Okay. So, and this is what Einstein deduced. Right, so h nu, right, this is what we saw 2 slides ago. Energy equals h, Planck's constant, times nu, the frequency. This is the photon. This is the light that's going in. And this is actually an example of conservation of energy. Each photon has some energy. Once it hits the metal, that energy gets absorbed. Once that energy gets absorbed, what happens to it? Well, some of it goes into what's called W. W is a work function, and that describes how tightly the metal is holding the electron. So that energy first goes towards knocking the electron out, overcoming the energy that the electron is being bound with. And then, once you've knocked it out, whatever is left goes into giving that electron some of its own kinetic energy. And so if h nu is less than W, right, if h nu is less than W, there's no electron coming out. If h nu equals W, then there's an electron coming out, but the kinetic energy equals 0, right? So it just kind of pops out and nothing happens to it. If h nu is greater than W, then then an electron pops out with a certain kinetic energy. And what's the kinetic energy that it pops out with? Whatever's left, h nu minus W. Okay, so
Wait, so if h nu is smaller than W, Ke is 0?
well, there's no electron that comes out, right? So let's say I should have okay. Okay, let's say I'm the metal and this is the electron. Hit the eraser. Nothing happened, right? The Ke of the incoming electron or the incoming light was not high enough. Or the h nu, right? The energy of the incoming light was not high enough. Now hit it really hard, right? So now she hit it harder. That means that the nu got higher. And so it knocks the electron out, but it didn't really go anywhere. I don't know where the eraser went. I hope I don't have to erase the board anymore. All right, now hit it like you're really mad. Not me. So now she hit it really hard. The electron had a lot of energy, right? So she's the photon, right? If the photon's really wimpy, that means the nu's really too small. Nothing happens, right? Because I'm holding it with some energy, with W. If she hits it just with the same energy that equals to W, it knocks out, but it just kind of has no energy to go anywhere. If she hits it really hard, greater than W, then it goes flying with the energy that's left over, Ke. Right, Ke. So if Ke is greater than W, this is what if h nu is greater than W, this is what the kinetic energy of the electron is, right? H nu minus W, whatever's left over from knocking it out. Okay. So let's do a problem. So we decided we're not, nobody likes you and we're not doing recitation today. But are you free on Tuesday? Okay, so we'll do Tuesday. Okay, so what is the longest wavelength that could cause the photoelectric effect in calcium, which has a work function equal to 4.6 times 10 to the negative 19th joules? Work function equals 4.6 times 10 to the negative 19th joules. Yep. And, right, 4.6 times 10 to the negative 19th joules. That's an amount of energy. So what happens, so it's asking for the longest wavelength. wavelength correlates inversely with frequency, right? So let's look at this. H nu, energy equals H nu, right? But nu equals, lambda nu equals C, right? So nu equals C over lambda. So if we take this and plug it in for nu, we get E equals hc over lambda. Right, so what does this mean? Lambda is in the basement here, it's in the denominator. As the wavelength increases, what happens to the energy? Energy goes down, yeah. So if the wavelength is smaller, the energy is higher, right? So wavelength gets bigger, the energy gets lower and lower and lower. So what's the longest wavelength that could be used to cause the photoelectric effect if the work function is this? We have to find, what do we have to find then? We have to find the lambda that has an energy associated equal to that. So what's H? H is something you won't have to memorize, but it's Planck's constant. But again, if you're doing it right, by the time you come to your exam, you'll have it memorized. H equals 6.63 times 10 to the negative 34th joules times seconds. So what do we want? We want to find the lambda, find the lambda of light whose energy equals W. Anything greater than that lambda will have an any light that has lambda greater than that lambda, the energy is going to be smaller than the work function, and it won't be able to knock out the eraser, right? It won't be able to knock out the electron. So how are we going to do this? We're going to take this, and we're going to say, what am I going to put in for E? Sorry? Yeah, the work function. So E is going to be 4.6 times 10 to the negative 19th joules. H is 6.63 times 10 to the negative 34th joules seconds. And C is 3.00 times 10 to the 8th meters per second. And solve for lambda. Look at this, right? So seconds and seconds will cancel out. And then I'm basically going to cross multiply kind of. And so I'm going to multiply both sides by lambda, divide both sides by this, and I'm going to get lambda equals 6.63 times 10 to the negative 34th joules times seconds times 3.00 times 10 to the 8th meters per second. I wrote out the seconds. And that's all over this. 4.6 times 10 to the negative 19th joules. So what happens? The joules and the joules cancel, the seconds and the seconds cancel. What we're left with is meters. And so lambda equals, did anyone actually do that? Equals 6.63 times 10 to the negative 34th times 3 times 10 to the 8th divided by 4.6 times 10 to the negative 19th. And so I get 4.3 times 10 to the negative 7th meters. Yeah.
What if I just, I did like E equals HB, so I divided H, so E over H, that's wrong.
E over
To
H.
find V.
Then you get V. But it's asked for a wavelength, so you have to convert V to lambda.
V to V, so now we got V, and then you use that equation, V equals C over lambda.
Yeah. You should get the same thing.
Okay.
Yeah. Questions here? Yeah. Oh yeah, then we have to change it to nanometers. So 4.3 times 10 to the negative 7th meters, 1 times 10 to the negative 9th meters equals a nanometer. And we get 4.3 times 10 squared equals 430 nanometers. Questions? All right. Yeah, let's take a break. Let's say we had same problem, right? If lambda equals 3.0 times 10 to the negative 7th meters, find the kinetic energy of the ejected electron. So same information, but if the wavelength is 3.7 times 10 to the negative 7th meters, find the kinetic energy of the electron. Okay, so put your heads together gently and give it a try. The H. Okay, let's erase all of this because this is going to confuse you. So what's the formula that you're going to eventually use? Yeah, that's in there. That's in there. But how are you going to find the kinetic energy of an electron? What's the formula with kinetic energy? H nu equals Ke plus W, or Ke equals H nu minus W. Yeah. Yep. What's that? Well, nu is related to C and lambda, right? Lambda nu equals C, and you're given a lambda. All right, let's do some work. You get it? Work. All right, so where we're headed for is this, or alternately this, right? These are really the same formula, just rearranged. So basically this is saying the energy with which the eraser got hit, h nu, equals the work function, how tight I'm holding it, plus whatever's left over, right, goes into giving the eraser energy. So in other words, the energy the eraser gets is equal to how much energy it got hit with minus how tight I was holding it, right? And whatever's left over determines how far and how fast the eraser goes flying. So what do we need to find? We need to find Ke. In order to find Ke, we need h nu. Can we find h nu? Well, sure we can. We don't know nu, but we know lambda, and we know that lambda equals c over nu. Right? So if we plug straight in here, we can do this and find the nu first, or we can plug straight in here. H nu equals hc over lambda equals 6.63, right, or 6.626 times 10 to the negative 34th. I'm going to run out of space here, joules times seconds, times I'm going to write smaller. H nu equals hc over lambda equals 6.63 times 10 to the negative 34th joules times seconds times c, 3.00 times 10 to the 8th meters per second. Look, the seconds is now in the denominator, right? All over lambda, which is 3.0 times 10 to the negative 7th meters. So look what happens. This is a unit, meters per second, right, in C, meters per second. The seconds cancels with the seconds here. The meters cancels with the meters here. And I'm left with an energy, which is what I want. So this is going to be 6.63 times 10 to the, what's the exponent here? Negative 33. Negative, no, plus 8 minus 7, negative 33 joules.
Wait, I wanted to know the denominator you added. That's where you get on the last one.
Yeah, I did. So well, it's in the denominator, I subtract the negative, right? So I will add it. So you're right. Okay, that's not right. So that's negative 19. Yeah, that sounds better. 10 to negative 19th joules. And so that's this. Right? So Ke equals h nu minus W. So equals 6.63 times 10 to the negative 19th joules minus W, which is given, 4.60 times 10 to the negative 19th joules equals 2.03 times 10 to the negative 19th joules.
So when you subtract them, they'll say it was like negative 30, 10 to the negative 30, and 10 to the negative 19. What do you do with the...
If it was, in that case, I would just put it into my calculator, right? I mean, you'd have to expand it out to put in all the zeros and see where they line up. Right? It gets kind of tricky that way.
But when it's like that, you just leave it on negative 19?
Yeah, right. Because if you can add and subtract if they're the same exponent, but if they're different exponents, you have to kind of expand them. All right. What's that? So, Carlisle was just saying in the back, right, once you get it, it's easy. This is true, right? This is true with basically all of chemistry. There's very few pieces that are kind of intrinsically difficult. The part is being able to recognize what you're looking at and being able to translate it from words into chemistry, into math, and not having anything lost at any of those, and then solving the math, and not having anything lost at any of those steps. So, right, go home and do 10,000 problems, and this will become easy. Okay, so this brings us to the concept of quantization. Okay, so yeah.
I don't know. I did it with other way where you plugged in the V equals C over
Lambda, yeah.
Do you get a different answer?
You should get the same answer. Yeah. Okay, so quantization is the concept that certain properties are not continuous. That is, they can only exist at specific values. So this is kind of contrary to a lot of things that we think about. Like, quantization is like you're going up a flight of stairs as opposed to a ramp. Right? If you're going up a ramp, if you want to go from like the first floor to the second floor, and you go up a ramp, you're going up in a continuous way, right? It's kind of smoothly increases from the bottom to the top. If you're going up a flight of stairs, that would be considered quantized, right? Because you go up one step, you take one step up, you go up one step, right? But you can't go up half that step, right? If you take half a step, you're going to fall back down. If you take 2/3 of a step, you're going to fall back down. It's only until you get to the next step, the next full step, that you can go up. And so that's makes sense when you're climbing stairs, right? But it doesn't really make sense when you're thinking about, it's very hard to imagine if you're thinking about, say, the energy of an electron, or the energy really of anything. Right, if you have, you heat the water in your pot, it's not like you turn on the stove, it's 25 degrees, and then you wait 5 seconds, and it goes directly from 25 to 35, and you wait another 5 seconds, it goes from 35 to 45. It goes up continuously, right? It goes 25, and it slowly increases. Over time. But when we start looking at electrons and other very, very small things, atoms, that's what it's like, right? So, when I was in school, and when we were bored in class, like you all are now, one thing that we'd like to do is kind of twirl a pencil or twirl a pen around my finger. And when you do that, the pen is kind of rotating, right? And so you can do it fast, you can do it slow, you can do it in between. You can rotate your pen at lots of different speeds and lots of different energies. What happens when in molecules, though, is that the energy of that rotation is something that's quantized. You can rotate it at speed 1, you can rotate it at speed 2, but nothing in between, right? And that's what comes out of the experiments that we talked about, plus a lot of other ones, right? So the first thing we looked at is the heated solid black body. That's the one we did a pretty lousy job at explaining, but and that's also the one that it's just kind of a general introduction, right? So the energy of electromagnetic waves is quantized. That's what kind of comes out of that one. Then the photoelectric effect, that's the one where we spent some more time on, right? Where we try to, it's a very good example of quantization. It's the electromagnetic energy has in addition to being wave-like, also has particle properties. And those particles we call photons. And that's also, in a sense, an example of quantization. Because when you think about light coming out of the sun or coming out of the light bulb, you don't think that there can be like a smallest unit of light, right? It just kind of comes. And you turn, kind of like the dimmer switch. You turn it down, it gets smaller. You turn it up, it gets bigger. But if we look at really, 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 really small amounts, we get these photons, which are just essentially the smallest individual units of light that you can get. And so this slide is going to come back, and we're going to sort of add things to it, examples of quantization, as we look at different types of experiments and different types of observations that people made. And so let me just make sure I know what I'm talking about. Okay. Yeah. So the next thing that we're going to get to is electrons. Right? Some of you were very eager to learn about electrons. Right? So when we take white light, like light from the sun, and we put it through a prism, right, or you look at it through the rainbow, you get the whole rainbow, right? You get red, orange, yellow, green, blue, purple, and it's not actually like the rainbows that my kids draw, where there's like a line of red and then a line of orange and a line of yellow, but it's actually kind of smooshy and kind of continuous, like the red just kind of fades into orange, just kind of fades into yellow, and so on. We observe it that way because smooshy is a very technical term, actually. No, it's not. You see that because there's lots and lots of different photons, and you're getting, or lots and lots of light there, and it's getting all mixed up. But if somehow you're able to isolate individual light of light waves with particular energies, then interesting things start to happen. So here's the example that we're talking about, right? So if you have a white light source, incandescent light, you get it through a small slit, you get it through a prism, you get a rainbow, right? Red to blue. But in some cases, you can have light that comes from these special lamps where you have, these are something like what we think about as, what we talk about as neon lights, right? Neon lights are, some of them have neon, some of them have different gases inside of them, but each element is associated with different color, right? So if you see, eat here now in all red, then that has a particular element in that light. And if you take a light like this, discharge tube, and you do the same thing, the light goes through a prism, you don't get a whole rainbow. What you get is lines of different colors. And those lines will be in the order of the rainbow. Maybe not all the colors will be there, but they will be discrete, right? They will be separated. They won't be continuous. That is actually a lab that you're going to. Has anyone done that lab yet? No. That's a lab you're going to do in 109, where you look at these discharge tubes and you observe what you observe, and you try to correlate what you observe with something theoretical. Right? This is what you were talking about in the beginning. That's why I said don't talk about it, because we don't know it, we haven't learned about it yet. Now we've learned about it, or we're starting to learn about it. Right? And so this is hydrogen, right? This is what we call the line spectrum, or the line emission spectrum of hydrogen. Hydrogen has a purple line, a blue line, a kind of green-yellow line, and a red line. These are also known as bright line spectrum, so emission line spectra, or bright line spectra, or bright line emission spectra. And, right. So these are all different all different elements, right? And you can see each element has a kind of a particular signature associated with it. And that has to do with actually its electronic structure. And we'll sort of take a look at that. So this is what I was talking about before. Right? This is if you want to go from here to there and from there to there, you can take steps or you can take a ramp, right? And it turns out that even though it seems like energy should be on a ramp on a sliding scale, on the smallest, in the smallest kind of realm, it's actually stairs, quantized. It takes a certain energy for, actually this could be electrons, this could be anything, to go from one step to the next step and one step to the next step. What we just learned can then be integrated or applied into this. Right? It takes some energy to transition or to move between these steps. That energy can be, in many cases, correlated to or given, imparted by some light. Right? Let's say you wanted to move an electron from this level up to that level. What could you do? Well, you could shine some light where the energy, or the h nu, or the hc equals lambda of that light was sufficient to cover that much energy. And on the other hand, let's say this green ball dropped from up here to down here. It's going from a higher energy to a lower energy. In the last chapter, we looked at reactions, right? And if something goes from a high energy to a low energy, what happens to it? It has to emit some energy. It has to release some energy. In that case, we talked about it being like exothermic. It releases heat. In this case, it releases energy, but the energy is often going to be in the form of light. And what kind of light is emitted? Light with the frequency equal to h nu, where h nu corresponds to that drop in energy. So line spectra, we haven't looked in detail yet, but show that matter also has quantized energy. I guess we're out of time. It's just getting on a roll. So we will do recitation on Tuesday. We'll do some. We'll use that to do some review. You have your test on Thursday. We'll continue also in Chapter 7 on Tuesday.